We are Team 14, and our project is Pick Your Park for Senior Design 2 at Clemson University. Our team consists of these 6 members. My name is Greg. I'm a computer engineering student, and my primary job was with the Raspberry Pi programming and the 3D printing.
I am Chandler. I'm an electrical engineering major, and my job in the project was to construct the scale model and do the PCB design.
My name is Jack. I'm a computer engineer, and I primarily worked on RFID programming and the system networking.
My name is Mason Young, and I'm an electrical engineer as well, and I'm doing the hardware integration and the calculations.
My name is John Broughton. I'm a computer engineer major, and I worked on the software logic and database integration.
My name is Emily. I'm a computer engineering major. I worked on SQL programming and user interface design.
Our motivation for the project is that at the university, parking has been a very big problem. A lot of us have long commutes, not because of the distance traveled, but for how long it takes to find a parking spot. Our goal for the project was to find a way to more easily know how many spots are available in all the lots on campus. This here is a clip of the lot that our small scale design is based on. For our small scale model, we have a few main aspects to the project. One of them being the force sensitive resistors to basically register when a car enters the lot as well as exiting the lot. We also have a radio frequency identification scanner. Basically that'll be associated with the car itself when you buy a parking pass. That also can detect for maybe a car that's going in and it's not supposed to. And we also have a Raspberry Pi basically to manage all of that data with the FSRs and the RFID scanner. We have a user application that shows the number of available spots in each lot in real time that you can look up on the internet, as well as an admin app for viewing and editing the data. As I said earlier, we have a small scale model to just illustrate our design and show proof of the concept. We have smaller RFID tags as well as little FSRs on our speed bumps to check for the detection. And of course, that data is translated to an online dashboard. This is a block diagram for our system. You can see we have the RFID scanner and the force sensitive resistors going to the Raspberry Pi. We also have the Raspberry Pi sending the data to the computer, which is then sent to the user app. It's also worth noting that there's an LED that the Raspberry Pi is connected to. That signifies when the lot is full for that given lot.
Regarding the hardware design, we had a power supply of 5 volts, 2 amps, 10 watts that would go to the breakout board, the Raspberry Pi, and the RFID scanner. The scanner would have communication with the tags while the Pi was communicating with the LED. The breakout board was going to the FSR, force sensitive resistors, and the analog to digital converter, which is the MCP 3008. The hardware design requirements, we had a power voltage requirements of trying to keep this whole system under 10 watts. So we did that by using a power supply of 5 volts, 2 amps, 10 watts. As mentioned previously, we ran 5 volt on the RFID scanner, Raspberry Pi, and analog digital converter ADC. The FSRs themselves are highly sensitive, so we used weight detection for that. The RFID scanner must also read the RFID tags for short distances through wood as well, because it is underneath our model. The PCB design was done through Eagle by Autodesk. On the left, you can see the board layout that was designed in that software, with the dotted line being a ground plate, with the red lines and blue lines being the wiring between the pinholes. On the right is the physical PCB that was manufactured by PCBWay, and that you can see the breakout board with the MCP 308 and the 2 pull-down resistors.
For our project implementation, we have the Raspberry Pi on the left, which is wired up to the analog to digital converter circuit on the right, as well as a 5 volt power supply on the right and a ground plane that connects everything to a common ground. And in the back, we have the SparkFun M6E Nano RFID scanner. Our RFID scanner is the M6E Nano by SparkFun. It operates on a 917 to 928 megahertz frequency band. We have it set at a 27 decibel transmit level, and it operates on the Gen 2 RFID standard. We connected this physically using a serial to USB converter, and it interfaces with the Raspberry Pi using the Mercury API Python library. Overall, we tried to get this working with serial UART, but we overall failed to achieve the performance that was advertised by SparkFun. For RFID tags, we used the recommended tags by SparkFun. However, they were small and they suffered from a poor read distance, so we eventually purchased the Yorongtech UHF Gen 2 tags that were larger and let us read at longer distances. The tags themselves have sections of memory that we were planning to write CUIDs to. However, when we were reading this, we found this to be an unreliable way of getting the information. So we used the EPC, or the electronic product code, which is unique for every RFID tag, which is then sent to the database and is related to a CUID. So in our scale model, we have the cars with RFID tags, our 2 force-sensitive resistors that measure the in and out, and a lot fullness indicator LED. The force-sensitive resistors are used for vehicle detections, and each strip is connected to an ADC that is triggered by the weight of the car. The code to manage them uses a multi-threaded system to make sure that none of them can overwrite each other. Some of the inconsistencies we found with the hardware was that the FSR detection is not always reliable for the lightweight car models, especially when we took the metal bodies off. And the metal bodies had to be taken off because they interfered with the RFID scanner. They were creating a Faraday cage over the tag that decreased the readability and made it so that reading our tags was almost impossible.
This slide shows some of the algorithms we used in our design. On the left is the algorithm flowchart for our Raspberry Pi connecting to our to the server, and then we have on the right, we have algorithms for connecting the database to the client. So we have the top algorithm shows updating the database, and the bottom one shows an algorithm for adding a car to the database. On this next slide, we have more algorithms from our connection file. We have a function checking if the lot is full. This function determines the logic for turning the LED on or off. And then in the top right, we have the algorithm for removing a car from the database when it leaves the lot. This next slide shows the user dashboard that students can log on and view how many available spaces there are in a given parking lot. It is color-coded, so it will be green when there are more spaces available and red when there are fewer. There are also admin dashboards that we created, so we could go in and edit the data that is displayed on that main user dashboard. This first database table shows the spaces occupied, including the username and which lot they are in. This next database table shows corresponding RFID, CUID, and usernames. And this final admin dashboard shows how many spaces there are total in each parking
our software
lot.
design requirements. For this project, we needed communication between a Raspberry Pi and a detection subsystem, communication between server and client, which gives us the ability to encode and decode packets of information. We needed a database with tables to store parking lot sizes, corresponding RFIDs, CUIDs, and usernames, and also the current lot occupants. We required functions to update the database when a car enters or exits the parking lot, live user dashboard to display available parking spaces in each lot, and we needed an admin dashboard to show and edit current lot occupants, legal and illegal, and the ability to host a dashboard on the website. This next slide, the software flowchart, shows an overview of our software and how it flows through its functions. When a vehicle is detected in and it's a legally parked car, it stores its username in a space table in the database. While illegally parked cars are stored in a lot, are stored in the same way, but their username is stored as all zeros. The same functionality occurs whenever a car is detected leaving, except it is removed from the database.
This slide shows our software design. It's just an overview that really highlights the Django web framework, interacting with our client.py module that we made. So it shows how the sensors and the RFID, how that all communicates with the Raspberry Pi, which sends information to our server, which through various modules, it will update the database that communicates with the HTML file on the website and displays the dashboards for both the user and admin sites.
So as you see in the video, whenever you actually enter the parking lot, it updates on the dashboard, and whenever there's too many cars in the parking lot and the lot is full, the red light turns on. So the software challenges and bottlenecks was determining which web framework for the user hosting and the admin applications. They ended up choosing Django, learning how to use Django, HTML, JavaScript, and CSS, and Python as well. Determining the SQL database to integrate, which was SQLite, and learning how to create the actual database connection in Django. Also GitHub, learning curves, and networking between the Pi and the actual server. For the hardware, choosing and learning the PCB software, which we chose Eagle by Autodesk, and learning the RFID scanner application programming interface, or API, for flashing the actual tags. Finding large enough RFID tags and supplying enough power to RFID scanner to make sure that the tags are actually able to scan through the wood, and making sure we appropriately bought the right size model cars for the scale model. So for future directions for this project, we decided that it'd be better to increase the time before the live updates or make the events more event driven on the actual database, making multiple exits and entrances and multiple vehicle detection subsystems, which would come with the entrances and exits, and making sure they're connected to a single server. Machine learning to predict future parking space availability for each lot, and 7-segment display to show the actual amount of available spaces, or something to do with the solar power to actually power the hardware. In conclusion, our scale model presents a solution to Clemson's parking issues. The FSR counts the number of cars in each of the parking lots. The RFID scanner detects which cars are illegally or legally parked. The user dashboard allows students to view the parking lot utilization in real time, and the administrative dashboard allows the database to be edited in admin view to see which students are in each lot.